Pleasure to introduce Emil Bjerrum-Bohr, who's going to tell us about string theory, scattering equations, and analytic gluon amplitudes.
Okay. Thank you so much for this opportunity to present some recent results. So I will talk about sort of a combination of these papers here. So it started really back in 2014 with some work with Paul Damgaard and Piotr Turkin and Van Ho, who's in the audience. And we've sort of worked our way through to the point now where we can actually work out very explicit gluon amplitude results. And of course, this connects to the greater theme of this conference, which is to look at general relativity from the point of view of geometry. So the main equation in all this work is really this sort of amazing equation that was produced by Cachaso, He, and Juan. And it's a couple of years old now, but it's still relatively new. And it consists of sort of a number of interesting pieces of a formula. So it has a sort of insertion of certain constraints, which are the scattering equations. And we will hear more about the scattering equations today, and also how we solve these scattering equations. But the scattering equations impose a constraint on these CIs that sort of talks to this integration here and fixes this amplitude at specific points. And then there's two factors here which are interesting for computing various amplitudes. One factor is like a trace factor that carries color information, but it also carries some kind of ordering information of the legs. And then this object, the Pfaffian, that can have it can sort of be a way in this formula. In this case, it's a scalar formula. If you have Pfaffian to a power of 1, it's a gluon formula. And if this formula, you have a squared Pfaffian, you have a gravity amplitude. And the implications of how these terms sort of interplay will be sort of the focus of this talk. And maybe it's worth mentioning that the Pfaffian here is really the only place where polarization and the momenta sort of appear. So a lot of the physical information sits in the Pfaffian. And another small thing to mention is that this is very alike these MHV traces we see in MHV amplitudes, where we also have a cyclic trace underneath. So it's like it feels like spinor-helicity, but in a very, very different form, generalized in some sense. And there will be a number of talks. There will be Ricardo's, Yvonne's, Peter, and Piotr's talk that will talk about various aspects of this physics that is inside this formula. But to start, just to introduce the subject, let's have a look at the scalar point amplitude. So for this endpoint scalar amplitude, that means we put s equals 0 here. We see that the Pfaffian goes away, and what we have here is just this form squared. All these cyclic factors square. So we get a square here. This is part of somehow how we gauge fix the integration. So I've written out basically the measure of the integration. And here's the remaining integrations that we have to do, fixed by the scattering equation constraints. So what we have to do first is to provide solutions for the SIs. So we put in these scattering equations and we find a solution in terms of the CIs, CJs. Once we've done that, and we can only do that if we fix these points, so we fix one of them to 0, 1, and infinity. That means we are now on the Riemann sphere with these points, and the points on this Riemann sphere that fix the amplitude are these solutions here. Then we have to sum over all the solutions we find here, so we do some kind of an average. And it should be mentioned that these solutions are generally really complicated, because these you can rewrite to some kind of polynomial form, but they will involve some kind of polynomials that has very high powers. And in general, these CIs are complex. So you'll have all these complex solutions with square roots, high-powered polynomial. But there's also some lure of, string theory in this. Like, for instance, this is very much like what we know in string theory as a Copenhagen gauge fixing. So the connection to string theory is basically two works. One in actually very early work by Fairley and Roberts. So they worked on these dual models, imposing these constraints, and they saw these equations coming out of what they did and tried to sort of compute some amplitudes. Especially Roberts' PhD thesis is very sort of illuminating. But these amplitudes they compute are not really what we are concerned about here. They relate more to this high energy limit of string theory, which is the Gross-Mendel limit. So it really is what happens when you take the string coupling to infinity. You get a string that's very energetic. And in that limit, the scattering equation comes out very naturally as the saddle point solutions of somehow the string action. In the other limit, where we do field theory, I mean, we have really no reason to impose these equations other than direct observation that this is something that works. So it was very nice to see first a proof of the formalism done by Dolan and Goddard, who are also in the audience. So they used BCFW recursion to basically prove that if you make this construction and you make a recursive proof, this works if you use complex analysis to fix the residues. And on another line of research, Mason and Skinner, and also follow-up works by Adamo and Casali and Skinner, and I probably forgot some references here. There's a whole literature now on ambitwistor space and how to basically see the scattering equation formalism as coming very naturally out of this formalism. And in the same way, you can also see the pure spinor formalism as a very natural playground for these scattering equations. And just to mention, so in order to solve the equations, which is something you have to face when you start working on it, there has been some recent work on doing explicit solutions. So it started really with Dolan and Goddard's paper. There's been some work on you write the set of polynomial equations down, and you can see this as an algebraic system. And if you apply some of these techniques that go for such polynomial systems like Søgaard and Zhang or Cardona, Gomez, Slotnikov, then you can actually make some headway with this. So this will be slightly different from what I will talk about today. But anyways, let's get started with a simple example. So the simplest example we can consider is really 4-point scalar scattering. So in that case, if we write out all the scattering equations, we have 3, but they are not independent. So we have to gauge fix 3 legs, so there's really only 1 leg that we can solve for. So we pick any of these equations here, and we make this notation that we can call S12 for S, S13 for U, and S23 for T. This is very standard old Mandelstam notation. We made the gauge fix, and we call the independent variable X, and then we just solve. So we see this 1, 2 is really X, 2, 3 is X minus 1. So we plug into the equation, and we see that the solution is X is S over S plus T. So it's basically a ratio of S and U with a sign. So now once we have the solution, we plug into the equation. So we put in the delta function that we have to put in. We have the measure, we have taken everything out. This is the integrand, it's the squared cyclic trace. And we have to, of course, account for the fact that this is a delta function in some function f of x. So there's a Jacobian associated with it. But anyways, we can map out what x is, what 1 minus x is, and then we put in the Jacobian factor. So once we have divided everything out, we have s plus t over s divided by st. So this is exactly what we sort of expect. This is a planar scalar amplitude. We get 1 pole in s, 1 pole in t. We have no pole in u because this is planar, so we're not expecting that. So now we could, and this is what we did the first, because this reminded us of string theory. So in string theory, you would just have something relatively similar. You would have the integration still. You would have no delta function. You would have a Kober-Nielsen factor, which is this alpha prime s and the 1 minus x alpha prime t. And then you would have a denominator which is actually 1 less than this cyclic function we have here. So it's the -1 we see here. So we integrate, we get gamma functions. So of course this is something else. I mean, this is not, but to leading order it is exactly what the scattering equation gives. It's 1 over s, 1 over t, and then you get a correction of order alpha prime. So, I mean, in the limit of alpha prime going to 0, this is the same, although it's a very different logic. I mean, here you're sort of integrating along a line. You have points in 0 and 1. In the other case, you have some kind of complex integration where you pick up certain residues. So what we thought was interesting was really that if this sort of connection between the stringy integration and the CHY integration can become sort of more manifest, we can use that to tell stuff about the two formalisms. And this is what we are sort of working towards. So basically the lessons are the following. In string theory we do integration along an ordered, in an ordered manner along the real line. So we fix the order by fixing the integrations. So we fix the ordering that we do in the integration. Whenever we have a pole, it's from a pinching region. So it's when two integrations start becoming very close, so the variables are very close to each other, you get a 0, and that is called a pinching. Once you have a pinching, the Copenhagen factor will split up some of these poles in a pole form. In the scattering equation formalism, it's really just an integral sort of you put in. You never integrate it because you, as soon as you see it, you saturate it by this delta function. So the amplitude is actually local all along. The solutions to the scattering equations are these polynomial equations, so they are not necessarily on the real line, so we can't really compare to what's happening here. But we still have this cyclic factor here that orders the integration. So the basic relation we are sort of looking at is something like that this ordering we see in string theory in terms of Heaviside functions we can put into the integration is like aligned with this delta function in the scattering equations divided by this cyclic trace factor. And outside we can sort of keep the same integration, so we can keep a Copenhagen factor, which we take to alpha prime to 0 in the end, and some integral h of z. And a lot of the work that I'll present today is really sort of using this interplay that sometimes it's useful to see the h of z as being here, and sometimes it's useful to see it here. But by using this kind of link or connection that we now know, we can use certain features that are useful in either formalism. So in this point of view, CHY is really just sort of like a very explicit truncation of low energy string scattering. And I believe that Piotr will talk a little bit about his newspaper that touches on to this. One useful thing is that in string theory to compute amplitudes, it's really hard because as soon as you have written down an integrand, you have to do integrations, and the integrations are really difficult integrations because you have to work out these gamma functions. And the problem grows. I mean, you get generalized hypergeometric functions very quickly. So you have to really be careful in how you organize stuff. And there is, of course, many works that show how you do this. But still, if you look at it from the point of view of having some kind of explicit formula where you just put in numbers, there is some advantages there. And one of the things that is very important in this approach that I'll explain is really this fact that we have that we keep the Copenhagen factor. So if we look at glue amplitudes, so the equation I showed before was the scalar case. We have this Pfaffian that has to be reduced. We have now a single cyclic trace, so it's not squared. We still have the same sum over solutions. So this is the Pfaffian. It splits up into 4 blocks. If you look at string theory, this is the object you would have to integrate. So first you would have to carry out all the supersymmetric or auxiliary fermionic integrations in theta and phi. Then afterwards you'd have to do the integration in Zi. And you see this is like an integration at endpoint, which is like n d sets. So, you know, this is, it's huge. And then in the end, you would have to take this delicate limit of alpha prime, in which cancellations occur as well. So certain terms have to combine in certain ways for this limit to make sense. So one of the places where the Copenhagen factor plays a role is really when you have in string theory transformations of integrands that use IBPs. So if you have a Copenhagen factor, now it's a 4-point, you apply a derivative, you get something out that is like the scattering equation. So you can take this picture that you go to the framework of string theory, you rewrite in terms of partial derivatives. If you go to the scattering equations, it's really like you put the scattering equation in somewhere that's like putting a 0 in. So you can multiply anything in front of that, and you can also split the two terms. One of the things we don't understand is that, okay, it comes from these IBPs, but I mean, we see no natural way to put in the scattering equations like a delta function in the formalism. But this is very useful for rewriting. So as I pointed out, there's like basically 3 current options for evaluation. So the formalism is there. We can write out the formulas, we can write out the Pfaffian, and we can insert whatever we want in these formulas. So if we solve directly in terms of numbers, we can do that. We see there's kind of like some threshold. When you get to like 7 point, it starts getting really hard. I mean, 6 point is manageable. You can get reasonably good, normally numerical results, but also you can get some integer stuff. When you get to 7, you really need something extra, and I think this can be pushed quite high. But the other thing is that you get numerical results. It's not very useful. You can't see where the poles are. You can't really sort of explore the amplitudes. So this is why we sort of set out this game for evaluating the residues in a different way by formulating these scattering equation rules. So I'll show you how this works and also how we extend this to gluons. And also, as I mentioned, there's these techniques for direct integration, which potentially could be another way to do this. It requires that one finds a very good way of handling polynomial division, which currently I think is also a bottleneck. So basically these two things are tied. The direct integration and these direct numerical solutions are sort of neck to neck. I think the direct numerical solutions are easier to implement but give less insight. The direct integration are possibly give more insight but are quite hard to implement in programs. So, but we are likely to see some progress here. But in the meantime, this is a very, very nice way of computing stuff. So for the scalar amplitudes, where we'll start, we'll try to make some diagrammatic rules just by looking at the diagrams that comes out of the formalism. So one useful way of thinking of these integrations is really by these diagrams where you draw lines between the points. So each line between a point is like a difference in two set i's. So for instance, up here we have a difference in 1, 2, we have a difference in 2, 3, and all the way cyclically to 1, 6. So this is a 6 point, this is the endpoint. So the endpoint diagram would just be the thing with endpoints around the edge. Now the interesting question we have here is really, can we start identifying individual diagrams in this amplitude? So you know, we know what this amplitude amounts to. It's phi cubed. So we could write it out in terms of poles. We can also integrate this and show that it matches the phi cubed. But can we sort of rewrite it in some way that identify the individual diagrams, and can we find some rules for directly integrating the terms? And the answer to this question is yes. So we go back actually to the formula I wrote before between string theory and the scattering equation solutions. And then we start looking at, in string theory, where poles comes from. So whenever you have a pole in string theory, it's because you have, you know, some set i's that come together in a pinching region. And the pole you get depends on how many poles come together in the same point. So for instance, if you have two legs, set I, set j, that goes to 0. That's usually like an Sij pole. If you have like a combination of a set I, set j, set k poles that come together in a specific way, you can get like a Sijk pole. So you can sort of make a rough counting on how this pinching happens. So it requires that one actually goes into this integration and defines or looks at how these pinching regions appear. But once that's sort of found out, we can take somehow the knowledge that we know about this pinching region and just drag it over here and see that the two different diagrams we have are the same, but the poles comes from different ways in the integration. But the count is the same. So we can take the count here, use the count here, and this gives us the scattering equation rules. So the easiest way to think of this is in terms of an example, but here I'll just present you the rough rule. So the thing is that if you have an integrand h of z, and now this h of z is really the common integral of CHY and string theory, it will have some arbitrary product of factors in the denominator, and each factor will have to satisfy some weight to give Möbius invariance. So for the h of z, you'd like that to be weight 2. Then when you do the integration, you'll get this product of poles, where each pole has somehow a factor of zi associated with it. If you have zi, just zi, and you do the counting of this factor, so you just have 2 points, zi, zj, and it comes in exactly the number of factors you see here, then that will give you a pole Sij. If you have some combination of factors Zij, jk, and this will be clear in the example that comes now, then you'll get another type of pole. And one additional thing that one needs to know is that when you look at these sets, they are kind of either nested or complementary. That means that when we take out a point 1, 2, we could just as well at the 6th point have looked at the number of points 3, 4, 5, 6. So let's do an example to show this. Yeah.
Scalar amplitudes are supposed to come from an open string theory?
So the scalar amplitudes are supposed to come from an open string theory. Yeah.
Which open string theory gives massive scalars?
Well, it's more like what you did like in dual models early time. I mean, you can find some integrations that will give you scalar amplitudes, like Joel Scherk showed that in some old papers. It's not so specific to a specific string. I mean, it's more like you have some integrand, and you have a Covey-Nielsen factor, and you know that if you integrate this right, you'll get some scalars out.
Can you tell me the vertex operator, what it looks like? Just so I understand where the OPEs come from. I can't figure out.
You probably don't need to be in a critical dimension or to worry about the absence of ghosts if you're just doing this.
Okay.
So you can just write down that there are plenty of dual models you can write down which don't have tachyons and have lots of ghosts and so on, which will suffice for this purpose. They're just the vertex operators look much as usual.
You don't need to have a consistent string theory, as Peter said.
I don't care about
just
that.
a rule.
I just want to know the OPE of the vertex operator, where this 1 over y minus z squared comes from. Then I'm happy.
You can do it with Kac-Moody currents.
That would give a 1 over y minus z, not the 1 over y minus z squared.
And also that's not an open.
Yeah.
But I mean, there's a single trace part from the single pole in the OPE of Kac-Moody currents, but also a double pole part, which are more complicated integrals, but which you can still cast into a basis of the single trace ones.
So that's where.
And you can do this with an open string and also with a closed string. So I guess also the sphere integrals will condense to the same W partial amplitudes if you set alpha prime to 0.
I think actually the exact string theory is not so important. All we want is an integration h of z that provides phi cubed, and we have that. But maybe we can discuss. Yeah. So just as an example, so this is a integrand that corresponds to this diagram up here. So in this diagram, it's a CHY diagram, so we've included the cyclic trace. This is the integration A of Z that you could integrate in string theory, or you could integrate it in the CHY formalism. So you see that there will be a double line in 1, 2, in 3, 4, and in 5, 6. So we look at the sets we have here. So we have sets is, the sets are 3, 4, it's 5, 6. Then we see that we have a set here in 2, 3, 4, because these things are connected by 4 lines. This corresponds to a set which is 1, 5, and 6 over here. And then finally we can have a set in 3, 4, 5, 6, which corresponds to the set 1, 2. And all we have to do in order to write down the result is really to find the sets that fit together, because that's the sets that in a pinching limit will give you a pole factor. So we see that 3, 4 is in the complement of 5, 6, and it's also in the set 2, 3, 4. So one combination that can give a pole is 3, 4, 5, 6, 2, 3, 4. Or the other option is we have 3, 4, again in the complement of 5, 6, but then it sits in the bigger set, so 3, 4, 5, 6. And that's the result of that diagram. So you get a pole S34, a pole 5, 6, you get a pole in 2, 3, 4, and a pole in S4, 5, 6, which we could also write as 1, 2. So it's basically, this is how you look at string theory and find pinching factors, and you just translate that into a CHY formalism. So now you can take any diagram basically which are of a simple type, so basically that the pole comes out from a simple pinching limit, and just write down the result. So here you have these sets here, and you see what the combinations are. So you see all sets should be something like 1, 5, and 6. This is that S here. Then you can have a combination with 5, 6 and 5, 6, or you can have it with 6, 1. And again, you can have a combination with a pole here, 2, 3, or with 3, 4. And down here we have a simple example of something that only gives one combination. There's only one combination of sets that will give us this pole structure. Or you have this diagram here where you have 5 different poles. But it's very easy to program this to make a machine that integrates these diagrams for you. So basically, this led us to sort of understand, when you have this double line diagram, how does that correspond to the Feynman diagrams? And in fact, it's possible to basically make a one-to-one map between the two. So you write down a phi cube diagram like this, and you directly translate it to its corresponding pinching limit. So you have like a 4, 5, a 3, and it meets the legs 1, 2, 5, 6, 7. So what you do is you write for each of these legs sort of a polygon picture, and when you put this polygon picture together and draw lines between points, so here for instance 2 will have to go together to 6. You see this line here becomes a 2, 6. 1 will have to go through here to 4. This is this line 1, 4. So you can directly, by making a polygon picture like we've done here, write down the corresponding CHY diagram. And this is how we can now understand how, in a way, CHY translate into Feynman diagrams, at least for scalars. And we can also see that the polygons we write down can be decomposed. So for instance, if we have something that is bigger than a triangle, so it's like a square, we can decompose that into triangles just by using partial fractioning identities. So this integration here, which is this, can be rewritten in these two terms, which is then partial fraction into this. So now you have this decomposed in terms of these two triangle diagrams. So we see that basically this is how phi cubed works. So we have a very compact way of writing phi cubed as the full double line diagram, but we can also decompose into the various contributions that we would see in Feynman decomposition. And one of the uses of this was basically that it makes it possible to extend this to other scalar theories. So basically any polygon is a vertex for a scalar theory. So if we want to say make phi to the 5th, we start with this amplitudes 1, 2, 3 to 5. We divide out the phi cubed component, and then this is a vertex we can use to decompose, for instance, an 8 point or an 11 point and so forth. And basically the construction is just by gluing these vertices together in all possible ways. So you get some diagrams like this, that phi cubed is really all the diagrams that consist of glued triangles in all possible geometries. If you go to phi fourth, it's boxes glued together in all corners. And if you go to phi fifth, it will be these pentagons and so forth, n-gons in the phi n. And of course there's some annoying feature of dividing out the dependence of phi cube theory in order to make these rules work. But it is a way to explicitly extend CHY. So in order to go to glue, we have now seen that we can use these pictures. So CHY is very close to this picture, and this is the normal picture we see. We have seen for glue a lot of help in the fact that we can take individual vertices, so F, A, B, C's, and combine into traces. So this is very sort of a little bit alike the CHY way of doing stuff. So now what would be interesting is really to see how this happens in glue. So when we write down a glue amplitude and we write it in terms of these CHY diagrams, we sort of think of the string theory limits as something like this, but now we actually want to split that up into contributions of these kinds. So how can we do that? And in fact, this problem of providing analytic trees for Yang-Mills is a quite difficult one, because I mean we're used to using spinor helicity, which simplifies things a lot, and the only really possible ways it seems is to use recursion like Behrens-Giele, or we can use string theory in some arbitrary dimensions, and Oliver has some nice work in that direction, but still it's quite complicated to proceed. So here the scattering equation formalism at least offers this promise that it might actually be a very nice way of doing things very explicitly. And the key aspect here is to avoid integration. So for gluons, the starting point is this integrand, which is of course is much more complicated than the scalar one. So this factor has simplified with one factor, so this is now just cyclic. This Pfaffian here is a big complicated object. So we have to write it out in terms of reduced Pfaffian that removes one line, one column. Then these matrices A and B and C will each have sizes which is like at 4 point it will become like an 8 cross 8 matrix that under the reduction is a Pfaffian of a 6 cross 6. At 5 point you have like a 10 cross 10, which makes a Pfaffian of an 8 cross 8. And in each of these components we have stuff like Sij divided by an insertion. We have the polarization Eij divided by an insertion. And then we have terms that goes like epsilon dot k. So terms of epsilon dot k is what sits up here in the C matrix. And there's a diagonal component as well, which corresponds to the fact that I and j can in fact be equal. And the result of that limit, which is in some sense a singular limit, is this factor. This is given by the CHY formalism. But if we put this in and we compute the Pfaffian, we directly know what we have to compute. Then we just have to take this integration, divide by this cyclic factor, put in the solutions, and we have the result. So when we start working this out, we see we get two types of terms. So we can have either terms that involves contractions of the polarizations, and we can have terms that involves all factors of polarizations and momenta. In fact, the terms that comes with polarization and momenta are the easiest to deal with, because they come from the part of the Pfaffian that sits in so A and B. A has all the Sij's, B has the Eij's, and the C has all these epsilon I dot kj. So we know that we are in the C matrix when we reach these points, and they tend to be, we don't, for those terms, we don't see like so much squaring of poles and things like that. In these terms, we have some kind of Pfaffian of A, Pfaffian of B, and in that we have similar insertions. For instance, if we have an S12 and an E12, we'll get a double pole. But we can split into these two types of terms. But one very nice thing we see from the Pfaffian straight away is that it's always multilinear in the polarizations. And if we have the factor here of how the epsilons and the k and the so forth is contracted, we kind of know the integration down here. So we can basically use the numerator to reconstruct integrations. So the problems we deal with, which is manifestly different from the scalar type, is that in the scalar type all we had was these double line diagrams like this, and they follow very simple string theory pinching limits. As soon as we go into the gluon regime, we get stuff where we can get things that are quadruple, and we have also or cubic, and we also have lines that cross like this. So this is a very funny corner in a pinching limit, because it kind of has too many singularities for it to be for the limit to be consistent. So we have to do something with diagrams like this in order to integrate them. And finally, there are some integrations which are funny because they come from the diagonal components. So whenever you have a diagonal component, it's like, say at 5 point, you have some trace, and the CI, which is now 5, 5, will be like a trace you have of these legs here and a single point up here. So it's like these connections here are missing in this term. So we have to do something with these terms in order to rewrite them. So it turns out that the diagonal terms are actually quite easy to deal with. And the fact is that because we have E dot k in them, we also have momentum conservation identities. So an E dot k, of course, contracts with a, so an EI contracts with a ki and gives 0. But we can write that ki as a sum of all the other momenta. That means we have an equation for epsilon ki. If we put in that equation in this ci term some random place, we get an equation like this, and this allows us to rewrite a diagonal term in this way. And now we see Möbius in a way this is restored, because we have now a line between ci and ci, and the extra factor we have introduced, a and l, is compensated by a numerator. So we have converted the problem of having non-Möbius invariant terms to having stuff that involves numerators. So now we can write down an integration. The only thing is we have to just look at the pinching limit again and see if we can deal with terms that involve terms that has numerators. So an example is this integrand here, where 2 and 6 have a numerator. And in fact, turns out it's very easy to deal with that in a pinching limit. We write the same sets as before, so 1, 2, 1, 6, 2, 3, and 5, 6. We have the clusters of 1, 2, 3. We have the clusters of 2, 3, and 4. So we have 4 lines here. But we don't have a cluster now at 1, 2, and 6, because the dotted line removes, a line. So when we write this out, we just have to write out the combination that doesn't involve this cluster. So if we do that, we see that in this diagram is 4 different combinations we can write, and that gives us uniquely this result. So we can deal with numerator factors as well as denominator factor on an equal footing. Now, the other problem is the tuple diagrams. And here we will very heavily use this string correspondence again. So whenever we see a diagram like this, so this is basically as bad as it can get. We get some kind of line, we have a numerator term, and we can write down the, what we'll do is in these cases is we'll pull out the outer rim. So we'll pull out our outer rim like this, and we'll use this, call it a PT. And there's a sign here associated because we order these points in a specific way. Now the interesting thing is that we go back to this correspondence. So if we go back to string theory, don't care about CHY, write the same integrand we had that was a problem as an H of Z with a Copenhagen factor and integration, then we can use a trick to compute it. So as an example, let's look at the 4-point. So the 4-point decomposes in this way. We have a term from the Fabian that goes like an epsilon 1, 2, epsilon 3, 4. This has a triple line diagram. The rest of the contributions are all benign, so they are all of the scalar type. This we can integrate, and all these we can integrate. So the result of this is basically that we have this integration, we write down the coefficients right away. Now we have to deal with the triple line. So what we do is we put that triple line into the string integration, and we write out the various ways of looking at the orderings. So we have these kind of identities that allows us to write out all the ordering with complex phases. These are called monodromy relations in string theory. And the H of Z is the same, but the sign of the Copenhagen factor makes these phases attached to the integrations. And what we know is if we integrate over the whole thing, we have to get back to 0. So if we look at this specific term with two triple lines, and we actually flip the middle line around, we can make this have phase 1. Then the diagram that has two triple lines will have phase alpha prime 1 alpha S1 2. And the one that comes after this, which corresponds to a different integration, so we have moved this line to the middle, will have this phase. So now all we have to do is basically split up in the two possible ways. So there's some ways of doing this in string theory using monodromy. So you can look at the real part, and the real part will give you a phase factor for this diagram of 1 and cosines. So when alpha prime goes to 0, these are just sines. And the other part is to take imaginary parts, in which case this diagram has no phase, so it goes away. And the sine is just basically sine to the alpha prime S12, sine to the alpha prime S12 plus S23. But this has to be 0. So now we have a link between this and that. So all we have to do is divide out this phase factor identity, take alpha prime to 0, and we see now this, we have gone back to the CHY perspective. So at this point, we left the integration of string theory. So we've started in string theory, we wrote it in, we took that expression, wrote it as a CHY expression. So basically we did the integration CHY, but left the phases. And once we've written out the real and the imaginary part, we can now just work in the CHY language, which means that we have a result for the triple line. So now we can just go ahead, write down the 4-point amplitude, just by taking the parts we knew how to integrate and add the part using this limit. And this, of course, extends. So at 5-point, you have more complicated tuples. Again, it's easier if you use the PT notation. So what you do is you write down just the phase relation for the PT. And if you write that out, you see that it immediately gives you basically an identity. So when you divide out the PT limit, you can write 1. So how to remove line 1, 2 in this way. So this is, of course, a complicated relation. It involves this division of the PTs, and it involves these S factors. But it gives immediately identities like this. So for instance, if we remove lines 4, 5 here, we see that this is the combination we'll get. So this is the result of that diagram. So this immediately extends the integrations that we can do. And here's some relatively complicated examples, but they all follow the same pattern. Once we get to 6-point, we have to use a bit more generalized PT relations. So we have to use monodromy relations in string theory that basically takes two integrations at the same time and distributes them. So an example is this case where 2, 3 is an integration that sits before 4 and 5. Now we move the set 2 and 3 through. So this is known as an ordered permutation because we keep the order on 2 of 3 and 4 and 5, but we move them through in all possible combinations. And again, you see the phases that are associated with the orderings are very simply given just by the fact that we start with 1, 2, 3. Once we go here, we have to add a phase 3, 4 because there's a phase associated with moving 3 past 4. Once we get past 5, we have another phase. So now this S is 3.4 plus 5, and so forth. So that means we can write down a PT relation of a more general type where we have more legs that we want to remove at the same time in this form. And these we can also think of as cross-ratio identities, as Bohr did in his paper. So just a few examples. This is one of the most complicated diagrams we see at 6 point. So we have 2 of these tuples like this, and they actually distribute nicely into this form. So then after that it's just left to integrate. One of the things that happens is this kind of interesting phenomenon. So we start with some lines up here. Once we have done these manipulations, we end with diagrams like this. So they have no double line. So basically they integrate to 0. So there's a lot of zeros in this as well. So it might look a bit more complicated than it is in reality. So here you only get, for instance, 4 terms out of these 5. So by doing this, we now know how to compute these basically endpoint gluon amplitude this way. We did explicitly 5 and 6 point as examples because 6 point is quite hard. There's some results by Stieberger and et al. In the literature, and there's also some higher point examples, but this is very explicit in the epsilon.k and epsilon.epsilon. Of course, going beyond 6 point will be a bit more complicated in the sense that there will be more tuples, there will be more diagrams. The number of terms in the Fabian grows quite tremendously. But in principle, this program is valid. There should be no new caveats opening up. So I think at this point, I mean, in order to proceed, what could be very nice is sort of a better, more fundamental understanding of this scattering equation formalism. And one way to where one could start is really between this map here, because it seems to be very fruitful in the sense of we can do stuff in string theory and we can do it in this related picture. And I mean, is it possible to make this link more precise than this? So we have, of course, tried a lot to see if it's possible to in some way rewrite these Heaviside functions. There's some complications because, you know, this is something that in principle holds for all alpha prime. This is not. So it's really only under this limit sign that you can do something like this. So it is basically some fancy way of doing this limit that here involves doing the integration first, then taking the limit, and this which basically don't need a limit first. You can just sort of evaluate. But anyways, it is a mathematical identity, and maybe we'll know more after Piotr's talk. But anyways, I'm happy to report that there's now a clear way forward for many different theories. I mean, this doesn't just apply to blue. We could pick any theory and we can now use these methods to rewrite these integrations and find analytic results. And one observation is perhaps surprising, that the solutions to the scattering equations seem to play very little role. I mean, basically it's the form of the CHY diagrams that are important for how to write the solutions. So it's the Fabian, it's the integrand that is important. Once we know the integrand, we can more or less write down the solution from it. So one goal, which is very practical, could be to extend these analytic methods to many other theories. One could think of theories with masses, phenomenology. I believe that, again, string theory is a very nice laboratory for doing this. We can, in some sense, at least in some of these dual models, put in masses for various scalar terms and extend these things to to massive scalars and stuff. So it should be possible to do a lot of different theories. And there's of course also the interesting aspect of doing general relativity and gravity. So here we have a Fabian squared, so there's some work to be done in understanding how this Fabian splits up. We haven't really looked at this, but we believe that many of the methods here should just apply. And if we want to do loops, all of this, the rules and stuff, basically is very well suited for this, because there's nothing that prevents us from using the solutions we find also at loop level. So we can write down a forward limit, and once we have the forward limit, we can use some of these techniques like Q-cuts and stuff to proceed to full integrations. So I believe that this is opening up a very nice chapter for new investigations. So thank you for the attention. Yeah.
So I would naively have thought that gravity is the one that you should use as the thing to try to relate to string theory. So you chose scalars and gluons.
It's I think it's an easier place to start to do gluons than gravity. I mean, you have the ordering in gluons, which makes it a bit easier. But besides that, I think there's no real issue in going to gravity. I mean, you have to square the Fabians, so the integrations will look more complicated. You'll have to come up with some way of organizing, but we know ways like, KLT ways of organizing in terms of PT factors. So I think that's possible.
I think it's the important problem what you're working on, but I'm not sure that you're concentrating on the open string, and I'm not sure.
Okay.
One of the main mysteries is that it seems to be a closed string or something like a closed string. And
that could well be. I mean, the relations we see are just, it is. I mean, we have not been so model specific. I mean, what we wanted was to introduce the Copenhagen factor somehow, because we saw the IVPs working on the Copenhagen is linked to the scattering equations. Yeah. So having this in the formalism makes things a lot easier. And it's also, the Copenhagen factor that allows us to use monodromy and other things. So there's, some very nice stories there. But I mean, I believe that if we write down the gravity theory, probably there would be a similar link between that theory and a closed string. And I think probably there's dualities between those closed string formulations and some open string formulations in terms of KLT and other things. So maybe the open string formula, this one, is maybe not the best starting point. I mean, I don't even know, should this be scattering equations? I mean, could one consider some other set of equations that could be equally good? I mean, the scattering equations themselves for this formalism seems just to be a nice way of organizing the information. But is it a fundamental fact that it's delta function of scattering equations? I mean,
I think it will go through literally for closed strings.
Yeah.
I mean, instead of the monodromy relations on the integration domain, you will have IVPs on the corresponding anti-holomorphic Park-Taylors.
Yeah.
So I think all the manipulations go through one-to-one. I think it's already there. In what you have done.
But that would be basically like some kind of KLC.
It's directly jumping to the single-valued projection, like to go from an open string integral to the closed string integral. You do a lot of violence to the alpha prime expansion.
Okay.
But to the field theory limit, it's absolutely harmless.
Okay.
The single-valued projection doesn't touch the field theory limit.
Okay.
And this is what is needed for the connection with CHY.
Any questions? Oh, let's thank you again. Okay.